Hello everyone, I'm Ashley and come from my network. Now I'm the head of R&D in my network. Actually, it should be Christian. He started first, but he's a bit late. So I will do the first part and he will be responsible for the second part. So my network is FHE restaking layer for AI networks. And we will use the FHE to do the revolution for the proof of stake validation. And the reason that we start this idea is based on some talks and some research by the Vitalik. Vitalik mentioned that voting is actually a very important use case. And this is exactly happened with ZK snarks. We have ZK snarks, so we can do the voting in a fair way and in a privacy-preserving way. But he mentioned in the 2024 Hong Kong Web3 Festival that if you want to get more and best property, especially the security property, then the MPC and FHE are what you have to use. Because FHE and MPC, as you know, that FHE is a Swiss knife of cryptography. So it's fully encrypted and it can provide the best encryption and the best security properties with all the schemes. So based on this idea, we have a restaking layer for AI and POS networks. And as we can see from the left side, we have basically 4 properties. First one is remote staking. We can support some secure token economy by ETH or by BTC, LST, LRT, and AI blue chip tokens. And the second one is our most important one. This is our scheme, support the consensus security. So this is protected by FHE validation network, which is exactly with FHE private voting. And the data protection by FHE, we can support end-to-end encryption for the validation process and PMF. The AI DP network, EigenLayer, AVS, Bitensor subnets, bridge, and more. So the left hand, it's more detailed pictures. So we have the left part, we have 3 layers. So basically 3 buttons here. The security layer, which is FHE validation network. The consensus layer, which is our mine chain. And the thing that today we just launched our TGE. So like a big day for us. And also the above button is a restaking marketplace. So the security layer, for which responsible for FHE validation network, we will cooperate with AI or POS networks such as Bitensor subnets, GPU farms, agents, AVS, and all other AI agents. So we will provide the FHE validation, and in a return way, they will provide our validation fee. And on the upside, it's the restaking solution. So for the restaking marketplace, like ETH, ASDR, TBTC, and all other AI frameworks, these blue chips, they will provide remote staking. And in return, we will give our staking yield. So this is our overall layer and overall framework for the AI and the POS networks. And go to more technique and details. So what's the problem we are solving? We say that we are a consensus security layer, leverage FHE technology. But what exactly the problem? And what we found that actually it's a research question from the Bitensor. When we see the Bitensor network, they have the miner and the validator. So it's a challenge and response process. The validator, the miner gives the challenge to the validators, and the validators will respond to the miners. And then all the validators, they will send the score to the Bitensor chain for the consensus, to the consensus layer. However, there are 2 key questions here. So first of all, everything is public. So validators can copy the score from other validators. So it's a free riding. And there's no privacy protection in this case. And the second one is that subnet, its domains might be domains by miners from a single entity. So actually, they are totally different, 2 problems. First, it's more like how we can provide a more secure and privacy-preserving way. And the second is that how we can make more decentralized and decentralized staking or validator community members. So we are trying to solve the first question. So this is our solution. So here we have still the miner and the validator. So the miner and the validator will still have this challenge and the response process. And instead of transmit the plain text to the consensus directly, we will use fully homomorphic encryption scheme. So these validators, they will use the same public key to encrypt the score. And once the score are all encrypted, it will generate the ciphertext. So we will have different ciphertexts. And the ciphertext then will be sent to the encrypted score, to the consensus. So instead of working on the plain text, the consensus will be calculated based on the encrypted data. And then, very similar to the Phoenix, we also have the MPC shareholder FHE, because this is to ensure that a single party can decrypt the value. So we have our shareholder validation decryption stats, and they were managed for the MPC multi-party computation for the decryption. And once we get all this decryption, the plain text we will recover the plain text consensus, and based on the consensus, we will distribute this reward, also distribute like reward distribution to the subnets, to the validators and to the miners based on our strategy. So this is our solution, FHE-based consensus with FHE. And this is how our ecosystem looks like. Now we have FHE AA and FHE other with DePIN and blockchains such as IONET, Bitensor, Zama, and MyShare. And also we provide validations with our mined single independently validation SDK. And in the up layer, we have these chains like Babylon and EigenLayer, they support for the remote staking. So this is how our ecosystem looks like in the current stage. And today, actually, we are focused our one-for use cases with Inco. So we are working on the secure bridge. This is another one we will leverage FHE DKSAP. So we have a lot of publications actually already on the market, already on the public, and also you can see from the internet. FHE DKSAP is a privacy-preserving transaction protocol that actually is our first product. And this we presented in the EPF Day, cohort 4, actually it was last year. Exactly with full homomorphic encryption based on dual key steals address protocol. And we also have this research paper published in the information science. It's almost will be online soon. And we have the article in Easy Research with more than 2,000 reviews, views, and with this FHE-based DKSAP, we also have one of the first Singapore Hackathon ETH. So that's how the process works on. And for more demos and docs, you can find on our website and our community with My Network XYZ. Thank you. And I want to ask, is Christian reached?
All right, thank you, Ashley.
Okay.
I don't think Christian is here, right?
No. Yeah, but if he hasn't reached, so I can answer some questions from technical parts.
Okay, yeah. So any questions for My Network? So maybe just high level, right? This is obviously a technical question.
Oh, no. Yeah, so if no, then actually I can share a bit more with Zama, our
oh, yeah, sure. Yeah.
Yeah, because we actually have another. So today also have another Zama event, so that's why. So actually we have another use case with Zama. we have the officially contract signed. How to build FHE AI. So this is another topic maybe most of us interested in. And maybe you heard that Zama is an open source cryptography company building on the state-of-art fully homomorphic encryption. And they are for solutions for blockchain and AI. And they have raised 17.3 million in a Series 1 called by Multi-Coin Capital and Protocol Labs. And the Mine Network is Zama's strategy partner right now. So this picture is exactly show how Zama have their libraries. Definitely you know that there is they have FHE VM, the concrete, and the TFHEIs. It's based on the Roost. So by cooperating with Zama as their strategy partner, actually we have our product with Zama Network. So with Zama and Mine Network, they're exactly our solution, how we can support FHE AI using their concrete library. So it's a quite complicated and a diagram for that. But in this slide, you can find more detail that we exactly will use the concrete from the library, first of all, to prepare the training data sets, and then to training a neural net models. And we will use this to compile into a FHE model and distribute to the compile FHE mode. So this is from the model developer. And the second part from the model hoster, that the model hoster will load these models, and they will this model hoster will make prediction by the encrypted value, also will respond to the encrypted prediction. So there are two parties, but in the left hand, we have the model consumer. So the model consumer will just, so it's more like an inference process. And we have the model consumer load the models and to generate the FHE key pairs exactly from the concrete ML. And we will encrypt the values. Like here, it's x equals to 2. So we will encrypt this x for the model host to predict it. And in the end, the decryption will happen with the secret keys get from the model hoster. So this is a process that this is a diagram. Exactly will be the first FHE AI product cooperated with Zama, proposed by Mine Network, and we will leverage their concrete library to conduct this framework. So this is basically what's our diagram, and but based on that, we will also reach the POS. As you can see, is the FHE validation. So the validation is already what I explained. That's our validation network, and this is our solution based on that. So in the we will conduct this FHE AI, and then we will reach the consensus for them to get the result, the predictions of the training or something. So this is also on the very beginning of the cooperation, our first picture of how our technique looks like. But yeah, but in the future, I think there's more. And so when FHE AI meet FHE validation, there are some questions like if data is very sensitive, then FHE AI is must to have. So what if we have like a credit score history from the records, customer behavior, wallet history, and tax reporting? All of this, then we have to recall what our challenge is and what is our opportunities. So FHE AI and FHE validation, in a summary, that we have opportunities because it's end-to-end production of model IP, user data, and the predict results. It's fair and verifiable validation. It also reduces the node requirements for trustable consensus. New paradigm is coming. But for the challenges, definitely the FHE computation speed needs more optimization and acceleration. And it has a learning curve in a short of talent. More awareness and adoption. Zama FHE AI support limited number of deep learning models. So they are all our challenges we are going to try to solve in the future. And yeah, so that's all from my side. And let's work on Christian from our BDT, and he will do more.
Yeah, I'll go into some of those. We are very excited about ultimately what we think we're building toward. is FHE LLMs, specifically in FHE and AI. We're probably a few years away from that due to a hardware acceleration. But what my network is focused on now is the next steps to build toward that. So let me get into presenter. All right, so welcome. Thank you, everybody. Ashley is our head of research at my network. I'm head of BD partnerships, so the non-technical co-founder based in the US. But what I'm going to do is build on what Ashley just presented on and show you how we're using those schemes now and addressing trying to tap into FHE as well as also deal with the limitations of FHE. So we know that we have a performance issue. FHE right now cannot deal with high speed, high transaction volumes. So what my network has been tasked with for the last year and a half is finding places where FHE is performant and has areas where there's already a window of time for something to be achieved, for a task to be achieved, in which we can perform the FHE computation without actually slowing down the overall system and processes. So I'll talk a little bit about the products that we shipped that brought us to where we are today. We started out in the end of 2022, building a decentralized data lake, an FHE data lake. And so the idea was that users in Web3 that are using decentralized data storage, like IPFS or Greenfield or Arweave, could have that data encrypted with FHE. And then also the ability to compute upon it using FHE. So the idea would be that the raw data is never available to any third parties. Everything is stored in ciphertext. And so the concept was very popular and really well received. And so we shipped that product, and it was well received by DeFi and some deep-in players. The issue was that decentralized data storage is still a little slow for many users. So most of the industry is still using Amazon or Google for storage. And so we have a ways to go until we can actually scale up the speed in decentralized data storage. So we moved on to a second product rather. And what we found was that one of the most vulnerable areas in Web3 are bridges, very vulnerable to attacks. And there's a lot of now institutional money coming into the space, and they're used to certain protections and security that they have in traditional finance. So one such example is that if you're going to use SWIFT, the interbank messaging system, every single recipient of data to execute a transaction is encrypting the data, which is the information of that transaction. They're decrypting it to run their own processing and to verify, then they're re-encrypting it and sending it on to the next party involved in that transaction. But there's an intent layer that goes out to initiate every single transaction. So if you are a big bank like JP Morgan, sending funds to Credit Suisse or the like, these large transactions cannot be seen by all the banks involved. The risk there, obviously, is in addition to a data leak, if you have your plain text leaked, it's just the ability for a third party to front run any kind of transaction. So this is particularly relevant in Web3 because we know we've seen a lot of front running and a lot of MEV activity. So we were in the Chainlink build program. We were speaking with their capital markets team and the team that was in charge of building CCIP, which is Chainlink's cross-chain interoperability protocol, which was really this bridge built on their Oracle network, their decentralized Oracle network, to help big institutions transfer assets into public chains and back again. So when they were running this test last summer, they discovered that everything was working smoothly from a technical point of view, but the regulators that were working with the banks were concerned that the intent layer was not encrypted as it is in SWIFT, in basic interbank messaging. So we used FHE to create a shared private state for the intent layer. And what we found is that this was a sweet spot for FHE because while FHE still needed a little bit of time for this transaction, SWIFT users were accustomed to 5, 6, 7 days sometimes to execute a transaction. So if we could beat that, we would be a superior product. And of course, we can beat that with FHE. So we used a shared private state for the intent layer for transactions across bridges. And so this is something that we're also going to be developing with other bridges and for our friends at Inco as well as Phoenix. But again, looking for a sweet spot, looking for a large total addressable market, a place where FHE can be applied right now without any performance issues, we still were searching. And we stumbled upon this really great use case in AI. So some of our team are PhDs in AI and ML, and this is always where we wanted to spend a lot of our time. And so Vitalik Buterin, obviously founder of Ethereum, has been talking about this issue of private voting. And in the beginning, it was kind of the simple example was DAO voting. So this emerged several years ago. In DAOs, you have very influential voters that are influencing other voters. And all the voting is public. And so there was this really easy observation to make, which is that the lead or the most influential voters would influence everybody else, and there was an impact on the fairness of the voting. So we need to find a way to basically encrypt or make private the voting so everybody can vote the way that they want without any kind of consequences. And then we built on that to look for other areas where consensus needs to be achieved, which there are many areas, obviously, in decentralized networks where we have to come to consensus. That's the key departure from decentralized systems from centralized systems is constant consensus, mechanized consensus. What we found is that in AI, you have, typically in AI networks, you have validators, a network of validators that are ranking AI models. And there's already kind of a window of time. Sometimes it's 10 minutes, sometimes 20 minutes. It depends on the subnet or the actual network, but they allow this block of time where consensus can be achieved to rank a model. They decide the parameters of how to rank that model, but there's a consensus that has to be achieved. And all of those validators have this time where they're going to publish their results to rank the model publicly. So every other validator in the network can see these results. And we learned as being early contributors in BitTensor that this was a problem. And the reason for that is because if you were staking, for example, in the BitTensor subnet, in a BitTensor subnet, if you had a lot of capital staked, if you had many tokens, that signified that you probably had a lot of compute power, and you had a higher chance of actually getting the answer right or ranking the model appropriately, and thereby earning the token rewards for that verification. So a lot of the other validators would then copy the lead validator. And so we weren't getting accurate validation of models. This is a problem because if decentralized AI has any chance of actually competing with centralized AI or taking share, one of the key metrics is going to be model reliability and usability. So we need models to scale, iterate, and be very useful. And if they're not getting proper validation, then they have less of a chance of actually competing with their centralized counterparts. So this is a little bit of what we did with BitTensor. So we create a shared private state, again, for those validators to come to consensus. So when they do their computation, they're not sharing it publicly. This means that every single validator has to do their own work. So it's almost like a forced proof of work. In addition to that, we found that FHE computation for these validator nodes is actually better suited for AI. So the mechanisms in most POS systems is it's less granular. In other words, in a POS system, the output from a validator might be 1 or 2 or 3. But in AI networks, the output can be 1.112 or 1.113, and so it's harder to discern the correct answer. FHE computation actually is better suited for this. And when we found out that the subnets already are creating this 10 or 20-minute window to come to consensus, we realized this was a sweet spot for FHE. The FHE computation will not slow it down. And obviously for simple like addition, subtraction, it's already performant, but if we need to scale up the computation or the complexity of the computation, we have a good window of time in which to do that. So this turned out to be a sweet spot. And this is a little bit of what that looks like. So AI validator networks can consume our SDK for FHE validation. And so this was a really cool use case. After taking it to BitTensor and getting a lot of a warm reception there, we brought it to Aether and IONET and Allura and Nimble and many other AI networks. And every single AI network that we spoke with said, this is a problem. We do need this service. Private voting is a really helpful use case for us right now. And we've been able to successfully orange pill many of the top AI projects into FHE using this solution. Our friends at Zama, also Inco's friends as well, Zama being the leader in the space in terms of providing cryptographic resources for companies in Web3 projects, they also are very interested and very keen to start building toward an eventual inevitability of an end-to-end encrypted web and also fully encrypted AI processes. So what Zama brings to the table now is a concrete ML SDK, which is built for model making and model hosting. So miners, developers can build their models or host their models where they protect the data inputs and protect the parameters that are training the model. My network brings the other side of the table where we bring FHE validation of those models. So we are building together with Zama toward an eventuality of a fully encrypted AI network. So right now it's a hybrid solution, but over the next couple of years we hope for this to be fully encrypted. These are some of the partners that we've brought on board. So Consensus Security is so the partners that I just mentioned are basically our customers. So they're going to be paying us to consume our FHE validation node. And then on the data security side, with projects like IONET, there's a process where there has to be consensus achieved among where do we source compute for a query or for a requester. So if you go on the IONET and you want to select a certain cluster, there has to be consensus achieved around, well, where do we get that compute from? And so this is another area where it was pivotal to have privacy for IONET. And this is the way that we partnered with them. Another really interesting use case, there's two other really interesting use cases of creating a shared private state to come to consensus in AI. One is SuperSite, which isn't listed here, but SuperSite is taking a query from a user and then sourcing all the different LLMs that best service that query. So all the nodes in the network have to come to consensus around what is either the best answer after querying all the LLMs, or what is the best LLM to go to. So in this case, again, to increase the security and increase the quality of the output, if we can create a shared private state, we force all the nodes to do their own work. Again, kind of like a mandatory proof of work. And then the second use case is with Allura. So Allura actually and Magnet AI are both interested in the same part of the AI process, whereby they want to help miners, developers in AI, bootstrap their ability to earn revenue. And this comes in the form of allowing miners to protect the inference generated from their models, to keep that as sort of IP. So if you've been following ChatGPT 4.0, you'll know that ChatGPT 4.0 was built off the inference from ChatGPT 4. So they took all of our prompts and all of our information that we used to prompt their model, and they built a new product. And so what Magnet is doing with their Modify economy is attempting to help miners punch up and protect more of the data that's created from their models, allowing a single-off developer to be able to compete with maybe an enterprise or a big company. And so this is yet another area where achieving consensus or creating a shared private state helps in the overall AI ecosystem. And so I will not go in so much right now to our remote staking layer, but we are focused on fortifying AI in every way that we can. So we did build a remote staking layer. And the purpose of this restaking layer is to bring the security of Bitcoin and Ethereum based on EigenLayer's model and the other restaking models, bring these tokens to AI networks to give the validators better earning opportunity. So all these AI networks basically function as a L1, as a brand new L1 or L2. And so they have the same issue as every other L1 or L2, which is that in the beginning, there's a small trusted set of node operators. And it's hard to bootstrap and scale for a variety of reasons. You can attack, obviously, a network in multiple ways. But it's good for them also to have this shared private state just at the actual token economic layer. So we bring LRTs, LSTs, or staked Ethereum, staked Bitcoin through partners like Babylon to these AI networks so that if the price crashes, as it tends to do in crypto, those validators are getting rewards from another token to help them stay there and validate that network. So crypto economic security is just another way that we're helping bring strength and security to AI networks. And so just to kind of touch up a little bit on my network specifically, we left our testnet phase and was very successful. We had 650,000 connected wallets, very active community, 3.5 million transactions. The market really loves FHE. We've built up a community of about 800,000 members between Discord, Telegram, Medium, and Twitter. And there's a great retail response to privacy. There's a real tailwind, we believe, right now for FHE. Even though there's a kind of marked hostility from regulators around the world, it is something that many retail users and much of the market is very bullish on and really wants. They're seeing news all the time in traditional media outlets about data leakage and data privacy and owning our data. They're starting to get an idea of centralized AI and how much power and how much productization they're able to achieve by taking our data. So we've got a real tailwind right now in the media. We think that FHE is in the right place at the right time. We simply need to scale, which is a hardware acceleration problem mostly. And we also need to keep looking for sweet spots where there's already there's a window of time in a process of maybe 10, 20 minutes where some process is being achieved, like consensus, and we can actually do FHE computation without slowing down the overall process. And so that's a little bit about what we're up to. Thank you very much. Let me know if you have any questions.